Moving on to topic 10, normal distributions. We're now going to look at the normal distribution. It is probably, or actually we know it is the most important, widely used continuous probability distribution. You may have also heard it referred to as the Gaussian distribution. In this course, I'm going to stick with normal distribution. So let's take a look at couple examples first. And remember some things about quantitative data in general and observational unit, etc. So example 10.1, human body temperatures in degrees Fahrenheit. So we have the data for 130 healthy men and women. Take a moment, fill in what the observational unit is, the variable, and then come back. Okay, hopefully for observational unit, you said each healthy man or woman. And like I've said in the past, I won't necessarily write everything down. So please make sure you have that in your notes. The variable is quantitative in nature, and it's the body temperature in degrees Fahrenheit. Could we get, when I try to think if it's discrete or continuous, I think about if I had a more accurate thermometer, could I get more and more decimal places? Yes. So it makes sense to me, in addition to looking at the histogram, that it is continuous in nature and not a discrete random variable. Since it's quantitative, we know it's quantitative, we've already said that. Since it's quantitative, we know we're looking at a histogram. It has, in this case, if we look at the line here that was drawn, so there's all the data, and then a normal distribution, a normal plot was laid over the top of it. Would you say that it's fair to, or reasonable, to model the histogram with a smooth bell-shaped curve? And I'd say, yeah, it looks pretty good. Most of the data's in. There are some things that aren't in. But remember, we're trying to get the majority of the data. And it looks like it's pretty well approximated by the normal. On the other hand, looking at baseball salaries, observational unit here, what do you think? 2004 baseball salaries? Observational unit is what? And hopefully you think each baseball player, even better, each professional baseball player, because, little league players don't get paid to play. The variable, what's varying from observational unit to observational unit or from player to player, is their salary. And that's going to be quantitative. So once again, we're going to have a histogram. Now here's the histogram. And then we said, okay, well, we're going to overlay a normal curve that supposedly fits it as best as it can. Does this look like a good approximation of this data here? And you're like, yeah, maybe, probably not. It looks more to be like something like this. And that definitely does not look like a nice, smooth, bell-shaped curve. Remember, the normal curve is, the histogram was, if we're going to use a normal curve on a histogram, it's a smooth and it's bell-shaped. You may say, well, why are salaries? Couldn't we list out every single person's salary? Excuse me. Yes, but there's so many values that it would be hard to be continuous. You could have people who make just one or two, a penny off of each other. So that's why in this case, we consider this continuous. So looking at, for terminology, the distribution of many, but not all, quantitative variables can be modeled using the normal distribution. We'll talk about requirements for using the normal later on. But the normal distribution is continuous. Remember, binomial is discrete. This is a continuous distribution. It has certain characteristics. Its center is at mu. E of x, remember that is the expected value, is right here. And we call that is the character mu. Its standard deviation is the typical distance between the observations and the mean. Remember, to get the standard deviation, you take the square root of the variance. And we call that standard deviation little sigma. Little sigma. So the notation, if something is if a random variable is approximated well by the normal distribution, is x, given that it is approximated by the normal distribution. Here's the center and here's the standard deviation. Now, these curves, hopefully you remember from pre-calculus, if you look at these curves, you can tell that they have inflection points. In other words, the concavity of the curve changes. So a bell-shaped curve with peaks at x equals mu, so at these tops here, and inflection points, in other words, where the concavity changes as at mu plus or minus, and I'm just going to put 1 here so we're really clear that it's 1 standard deviation. Alrighty. On this example 10.3, there are 3 normal curves graphed below. We're going to label the axis, then make an educated guess for the means and the standard deviations. Now, on an exam, I'm obviously not going to have you guess, but this is just to get us warmed up and starting to look at roughly what's going on. So I'm going to label these curves A, B, and C first of all. And they told me that these are exam scores, so I'm going to label this as exam scores. Let's find out what the center is and the standard deviation is for each of these curves. Now, we don't have any way to do any calculations, so we're just going to be roughly eyeballing it. And like I said, I would not have you guess on an exam. But looking at A, I say the center is pretty close to 70, so let's go with 70. A and C have the same center. Hopefully you can see that in terms of where they are. And B looks like it's roughly around 80 for the center. Now, where they change concavity, roughly where they go from being concave down to concave up or vice versa, is right about, I'm going to say here. And looking at the chart, we see for A, if the center is at 70, this looks to be roughly 75. So I'm going to say that the standard deviation is roughly 5. Remember, that's how far away you are from the center. It looks like it's about the same for B. They look almost identical, so it's a plus or minus 5. C, on the other hand, it's much more spread out. Okay, so C is much more spread out for sure. And I would say that that is probably around 60 is that first where the concavity changes. So the standard deviation there will be about 10. So we know that A and C have the same, excuse me, centers, and A and B have the same spread, but they're all different curves. So remember, we have to look, when we're looking at quantitative variables, we look at shape, we look at center, we look at spread or variance or variation along that x-axis as we look along the x-axis, and any unusual outliers. Now looking at I'm going to use C in particular. I'm going to draw C out to discuss this empirical rule. So I'm going to do a rough sketch of C. This is from above, and it was centered, we said, at 70. So I'm going to put the center at 70. And then we said, well, concavity changed around 10 out. So these are going to all be in just tens away. So our center is 70, and we're going to go down by 10 and then up by 10. That doesn't look very pretty, does it? Should have 100 a little further out, but you get the general idea. Maybe there are bonus points, so people got over 100 in this case. So I'm going to call this exam scores. And once again, I'm using roughly C from above. So I just moved it down here. And 100 is at the tail. I'm just going to move this out a little further. And I'll move this out a little bit further. Pretend that it's all nice and symmetric. Remember, this is just rough. About 68, the empirical rule, it's really helpful, tells us that about 68% of observations fall within 1 standard deviation of the mean. So we know the center here in this case is at mu is 70, so 68% of observations are going to fall right in here. We know 95%, based on the empirical rule, I'm going to change colors to make it a little more clear, are going to be 2 standard deviations away. So the area here, all in red, would be 95%. So of course that whole area would be filled in. And finally, 99.7, let's go for green. I know it's a little early to even think about Christmas colors, but work with me. 99.7, I'm going to put that 99.7% of all observations fall within plus or minus 3 standard deviations. What's the total area under the curve? Hopefully you remember, if this is a valid probability distribution, what does it have to be? Well, the area under the curve has to be 1.